Welcome to our comprehensive journey into firmware coding, where we'll explore the foundational concepts and practical tools needed to master embedded systems development. Whether you're a beginner or looking to deepen your understanding, this series will guide you through the essentials of working with STM32 microcontrollers, from architecture basics to hands-on configuration and coding. Let's start by setting the stage for what firmware is, why it matters, and how STM32 devices have become a cornerstone in the world of embedded systems. Get ready to unlock the secrets behind the code that powers modern hardware. STM32 family is one of the most widely adopted microcontroller lines in embedded development. Built around ARM Cortex-M cores, STM32 devices offer scalable performance, robust peripheral integration, and a supportive development ecosystem. Their versatility makes them suitable for everything from simple gadgets to complex industrial systems. In this scene, we'll introduce the STM32 family's core features, including their architecture, memory options, power management, and the extensive tools available for developers. Understanding these basics is the first step to effective firmware design. STM32 microcontrollers come in several series, each tailored for specific applications and performance needs. The entry-level STM32F0 and G0 series are perfect for cost-sensitive designs, while the STM32F1 and F3 lines provide mainstream solutions. For high-performance tasks, the STM32F4, F7, and H7 series offer advanced features and processing power. There are also ultra-low power options like the STM32L series and wireless-enabled models such as STM32WB and WL. Choosing the right series ensures your firmware meets both performance and efficiency requirements. Performance scaling is a key concept in the STM32 family. Each series is built around a different ARM Cortex-M core, offering varying clock speeds and feature sets. For example, the STM32F0 uses a Cortex-M0 core running at 48 MHz, ideal for basic tasks. The STM32F4 steps up to Cortex-M4 at 180 MHz, adding DSP and floating point support. At the top end, the STM32H7 features a dual-core Cortex-M7 running up to 480 MHz, perfect for demanding applications. Understanding these differences helps you select the right MCU for your project. STM32 CubeMX is a powerful tool that simplifies the configuration and initialization of STM32 microcontrollers. With its graphical interface, you can assign pins, set up peripherals, and configure clocks with ease. CubeMX automatically generates initialization code, saving you time and reducing errors. It also supports middleware integration and power consumption analysis, making it an essential part of the STM32 development workflow. In this scene, we'll see how CubeMX streamlines project setup and helps you get started quickly. CubeMX workflow is designed to guide you through every stage of project setup. It starts with device selection, followed by pin and clock configuration. Next, you set up peripherals and middleware, then generate the initialization code. Finally, you export the project to your preferred IDE. This structured approach ensures that all hardware and software components are correctly configured before you start coding your application logic. Let's walk through each step to understand how CubeMX accelerates firmware development. STM32 CubeIDE is a comprehensive development environment tailored for STM32 microcontrollers. Built on the Eclipse framework, it integrates a code editor, compiler, debugger, and project manager all in one place. With features like syntax highlighting, auto-completion, and version control, CubeIDE streamlines the entire firmware development process. It also offers performance analysis tools and direct integration with CubeMX, making it easy to move from configuration to coding and debugging. This scene introduces the key components that make CubeIDE a developer's best friend. One of the strengths of STM32 CubeIDE is its seamless integration with other development tools. You can import CubeMX projects directly, use the Cube programmer for device flashing, and monitor variables in real time with CubeMonitor. Static code analysis is also available to help you maintain code quality and security. This integration ensures a smooth workflow from hardware configuration to application development and debugging, all within a single environment. Hardware Abstraction Layer, or HAL, is a standardized library that provides consistent APIs across the entire STM32 family. HAL includes core system functions, peripheral drivers, low-level register access, and board support packages. It also integrates middleware for USB, TCP, IP, and graphics. Using HAL ensures your code is portable, reduces development time, and gives you access to extensive documentation and community support. In this scene, we'll explore how HAL simplifies firmware development and promotes best practices. Developing firmware for STM32 microcontrollers follows a structured process. It begins with project setup in CubeMX, followed by hardware configuration, code generation, and importing the project into CubeIDE. Next, you implement your application logic, then build, program, and debug the firmware. Essential prerequisites include a development board, the necessary software tools, a debug interface, and thorough documentation. Following this process ensures a smooth development experience and reliable results. Firmware is the lowest-level software layer that interfaces directly with hardware components. Unlike application software, firmware operates without an operating system and is stored in non-volatile flash memory. It's hardware-specific, requires real-time execution, and often involves direct register manipulation. Firmware acts as the bridge between hardware capabilities and system functionality, handling initialization, device control, timing, and power management. Understanding firmware's role is crucial for building efficient and reliable embedded systems. Microcontroller unit, or MCU, integrates several essential components on a single chip. These include the central processing unit (CPU), program memory flash, data memory RAM or SRAM, peripheral interfaces, clock management, and power management units. Each component plays a vital role in enabling the MCU to execute firmware and interact with external devices. Understanding the structure and function of these components is key to effective firmware design and troubleshooting. Firmware communicates with the MCU hardware through memory map registers and direct memory access (DMA). Key interaction methods include memory mapped I/O, register manipulation, and interrupt handling. The architecture of the MCU, including its instruction pipeline, register file, and execution units, directly impacts firmware design. Memory hierarchy from flash storage to SRAM and peripheral registers must be carefully managed for optimal performance and reliability. Instruction set architecture (ISA) defines the interface between software and hardware. It determines the available instructions addressing modes and data types that firmware can use. For STM32 devices, the ARM Cortex-M ISA features the Thumb2 instruction set, supporting both 16-bit and 32-bit instructions, conditional execution, and hardware multiply divide. Understanding the ISA is essential for writing efficient, high-performance firmware that fully leverages the MCU's capabilities. Reorganization is a critical aspect of firmware design. Flash memory stores the program code in constants, while RAM is used for variables, buffers, and runtime data. Stack handles function calls and interrupts, and the heap manages dynamic memory allocation. Proper memory management ensures system stability, performance, and maintainability. Firmware must allocate, protect, and optimize memory usage to meet real-time requirements and avoid fragmentation. Typical firmware memory layout includes several sections: the vector table for interrupt handlers, the text section for program code, data for initialized variables, for uninitialized data, and stack and heap regions. Each section serves a specific purpose and has unique size considerations. For example, flash memory is chosen based on code complexity, while RAM size depends on real-time requirements and buffer needs. Understanding these sections helps you design efficient and reliable firmware. Boot process is the foundation of all firmware operations. It begins with a power-on reset, followed by fetching the boot vector from flash, initializing the stack pointer, configuring system clocks, initializing peripherals, and finally jumping to the main application. Each step must be carefully executed to ensure reliable system startup. The order of initialization directly affects system performance and stability, making the boot process a critical focus in firmware design. For entering normal operation, firmware must configure all system components. This includes selecting the clock source, setting up the PLL, configuring memory controllers, enabling peripheral clocks, setting up GPIO pins, and initializing the interrupt controller. Each task is essential for ensuring the system runs reliably and efficiently. Proper initialization lays the groundwork for stable firmware execution and robust hardware interaction. Let's look at a practical example of the STM32F for boot process. The reset handler is the first function called after boot. It configures the system clock, copies initialized data from flash to RAM, and then jumps to the main application. This sequence ensures that all hardware and memory are properly set up before your application code begins executing. Understanding this flow is essential for debugging startup issues and optimizing boot time. General Purpose Input-Output, or GPIO, provides firmware with direct digital signal control. GPIO pins are the primary interface between the MCU and external components. They can be configured as inputs or outputs, with options for pull-up or pull-down resistors, output drive strength, and alternate functions. GPIO operations form the foundation of embedded system interaction, enabling everything from simple LED control to complex sensor interfacing. Basic GPIO operations include reading pin states, setting output levels, generating interrupts, and implementing debouncing. These operations are essential for interacting with buttons, LEDs, sensors, and other peripherals. Proper configuration and handling of GPIO pins ensure reliable communication between the MCU and the outside world. Mastering GPIO is a fundamental skill for any embedded firmware developer. Classic example of GPIO usage is controlling an LED with a button input. By configuring the appropriate pins as output for the LED and input for the button, firmware can toggle the LED state based on button presses. Debouncing logic ensures that only intentional presses are registered. This simple example demonstrates the power and flexibility of GPIO in embedded applications. Interrupts are a cornerstone of real-time embedded systems. They provide a synchronous event notification, allowing firmware to respond quickly to external or internal events. Interrupts are prioritized, can be nested, and require careful context switching. Efficient interrupt service routines (ISRs) are essential for maintaining system stability and responsiveness. In this scene, we'll explore the principles of interrupt handling and their importance in firmware design. Effective interrupt handling requires minimizing ISR execution time, using atomic operations for shared data, assigning priorities wisely, and optimizing interrupt latency. Interrupts can originate from external sources like GPIO pins, timers, communication peripherals, or system events such as watchdog timers. Firmware must handle each type appropriately to ensure reliable and predictable system behavior. Timers are essential for scheduling periodic tasks in firmware. By configuring a timer to generate interrupts at regular intervals, you can implement a simple task scheduler. For example, a 1 ms system tick can be used to trigger tasks every 10 ms or 100 ms. This approach enables precise timing and efficient resource utilization, which are critical for real-time embedded application. STM32 microcontrollers feature several types of timers. basic timers for simple counting, general-purpose timers for PWM and capture compare, advanced timers for motor control, and watchdog timers for system monitoring. Each timer type serves different firmware needs, from generating delays to controlling motors or monitoring system health. Understanding the capabilities of each timer helps you implement precise and reliable timing functions in your firmware. Figuring timers involves setting the prescaler value, counter period, count direction, and trigger sources. For example, in PWM motor control, you configure the timer for a specific frequency and duty cycle, then adjust the duty cycle to control motor speed. Proper timer configuration is crucial for achieving accurate timing and reliable operation in your firmware applications. Direct memory access, or DMA, allows data transfers between memory and peripherals without CPU intervention. This reduces CPU load and improves overall system performance. DMA can handle memory-to-memory, peripheral-to-memory, and memory-to-peripheral transfers, as well as manage circular buffers. Configuring DMA controllers properly enables efficient data handling in applications like ADC data collection or UART communication. Setting up DMA involves specifying source and destination addresses, transfer size, data width, priority levels, and completion callbacks. DMA is especially useful for repetitive data transfers, freeing the CPU for more critical tasks. Use cases include ADC data collection, UART data transmission, SPI communication, and memory initialization. Mastering DMA configuration is key to building high-performance embedded systems. Communication peripherals like UART, SPI, IDC, and can enable firmware to interface with external devices and systems. Each protocol has unique features and use cases. UART is ideal for simple point-to-point communication, SPI for high-speed synchronous transfers, IDC for multi-device setups, and CAN for robust automotive and industrial networks. Choosing the right interface is crucial for reliable data exchange. Implementing communication protocols in firmware involves managing state machines, data buffers, error detection, and timing constraints. Each protocol, UART, SPI, IDC, and CAN, has its own complexity and typical applications. For example, UART is often used for debugging or Bluetooth modules, while SPI is common for sensors and displays. Understanding protocol requirements helps you design robust and efficient communication system. See a practical example of IDC communication. Reading a temperature sensor involves sending a measurement command, receiving the result, and converting the raw data to a temperature value. This process demonstrates how firmware manages protocol-specific tasks, handles data conversion, and ensures accurate sensor readings. Mastering such examples prepares you for a wide range of embedded applications. Analog-to-digital converters, ADC, and digital-to-analog converters, DAC, bridge the gap between real-world analog signals and digital firmware processing. ADCs convert analog inputs into digital values for processing, while DACs generate analog outputs from digital data. Key parameters include resolution, sampling rate, reference voltage, and conversion modes. Proper configuration ensures accurate measurements and reliable system performance. Figuring ADCs involves selecting channels, setting sampling times, choosing trigger sources, and integrating with interrupts or DMA. ADCs can operate in single, continuous, scan, or injected conversion modes, each suited for different use cases. For example, continuous mode is ideal for regular monitoring, while scan mode handles multiple sensors. Understanding these options helps you design flexible and efficient analog data acquisition system. Monitoring battery voltage is a common embedded application. By configuring the ADC for the appropriate channel and sampling time, firmware can read and average multiple samples for accuracy. The measured value is then converted to a voltage, with corrections applied for voltage dividers. This example highlights the importance of proper analog configuration and data processing in real-world applications. Firmware layering is a design principle that separates hardware-specific code from application logic. The hardware abstraction layer, HAL, provides a standardized interface, enabling code portability and maintainability. Above HAL are device drivers, middleware, and the application layer. This modular approach simplifies debugging, accelerates development, and ensures your firmware can adapt to different hardware platforms with minimal changes. Hardware abstraction layer offers several benefits: hardware independence, code reusability, faster development cycles, simplified debugging, and a consistent API across devices. HAL abstracts hardware registers, provides peripheral initialization functions, and manages data transfers and error handling. By using HAL, you can focus on application logic while ensuring your code remains portable and maintainable. Well-structured driver architecture includes several layers: the board support package BSP for hardware initialization, HAL for register abstraction, device drivers for protocol implementation, middleware for system services, and the application layer for business logic. Each layer has a clear responsibility, ensuring separation of concerns and minimal coupling. This architecture enhances code quality and simplifies future updates or hardware changes. Effective firmware design follows key principles: separation of concerns, well-defined interfaces, minimal coupling, maximum cohesion, and clear error propagation. By adhering to these principles, you create modular, maintainable, and robust firmware that can evolve with changing requirements. Good design practices are the foundation of successful embedded systems development. Each layer in the firmware architecture has a specific responsibility. The BSP handles board-specific configuration, HAL abstracts hardware access, drivers implement device control, middleware provides system services, and the application layer contains system logic. Understanding these responsibilities ensures that each part of your firmware is focused, maintainable, and easy to debug or extend. Modular approach to firmware is demonstrated in the LED driver example. The HAL layer abstracts the hardware details, while the driver layer manages device control and state. The application layer uses these drivers to implement system logic, such as blinking a status LED. This separation allows you to reuse code across projects and adapt to different hardware with minimal changes. The application layer, you initialize and control devices using the modular drivers. For example, you can set up a status LED to blink every second and an error LED for fault indication. The application logic calls driver functions to turn LEDs on, off, or toggle them as needed. This approach keeps your code organized and makes it easy to add new features or support additional hardware. Throughout this series, we've covered the essentials of firmware coding for STM32 microcontrollers. From understanding the architecture and memory organization, to mastering GPIO interrupts, timers, DMA, and communication protocols, you now have a solid foundation. We also explored the importance of modular design and layering, which make your firmware robust, portable, and maintainable. These principles and tools will serve you well in any embedded systems project. As you embark on your own firmware projects, remember to leverage the tools and best practices discussed here. Use CubeMX and CubeIDE for efficient development, rely on HAL for portability, and structure your code with clear layers. Always consult documentation and reference manuals, and don't hesitate to explore community forums for support. With these tips, you'll be well equipped to tackle any embedded challenge. Firmware development is a dynamic and rewarding field. As you continue learning, you'll discover new tools, techniques, and applications for embedded systems. Stay curious, keep experimenting, and build on the solid foundation you've gained here. The world of firmware coding is full of opportunities. Embrace the challenge and create something amazing.